Hello, today it's my pleasure to talk about solving nonlinear multivariate equations. Of course, multivariate means that we've got more than one variable, so we have more than one equation, and they're nonlinear. So we're going to start with an example of a circle and an ellipse, intersection of those. We're going to remember our univariate rooting algorithms, the Newton-Raphson. We're going to remember our multivariate linear search methods. And then we're going to take those and kind of put them together and realize the multivariate Newton-Raphson technique. We're going to introduce the Jacobian, and then we're going to go back and take a look at that circle ellipse thing. So here we go. We've got a circle, F1. F1 is a circle when F1 equals 0. That's a circle. Then we have an ellipse, F2. When F2 equals 0, then that is an ellipse. So you see the functions, and you see that we have two variables. We've got an x variable, we have a y variable, and we put those as a column. It's column the vector. We call the column vector x under bar, or just x. And then we'll take our functions and put them as a column vector. So F1 and F2 are elements of our F vector, if you will. So there's a thing called a Jacobian. In a Jacobian, the rows will be the individual functions differentiated. So F1 will be the first row, F2 will be the second row, and these are partial derivatives since we have multiple variables. The columns will be in the order of the variables. So the first column is with respect to x, the second column is with respect to y. So you kind of see that if you think about F1 and taking the partial of F1 with respect to x, well, all you would be doing is just differentiating with respect to x, and you're just going to get the 2x right there for the partial of F1 with respect to x. If you look at F2, partial of F2 with respect to x, you're going to get 4x, right? You're going to get 2 times 2 is 4x, and all of the other terms kind of fall out in that column. If you take a look at F1 with respect to y and F2 with respect to y, F1 would be 2y. 2y is going to be in that first upper right location, and then F2 with respect to y is going to be 12y. So it's very simple, and then of course all the other terms go away, and that's going to be your Jacobian. That's going to relate the change in your variables to the change in your functions. So that's the idea. So here we know that our true solution in this simple one is x is the square root of 7/2 and y is the square root of 1/2. And you can see right clearly that 7/2 plus 1/2 is 8/2, so which is 4. 4 minus 4 is 0. And over here, if I had 7/2 times 2, that's 14/2. And then I'd have plus 6/2, so that's 20/2. 10 minus 10 is 0. So you see that is the true result there. And what we're going to do is, we're going to we're going to try to find that one particular root. But now this is a good example where we're going to have more than one solution. And Bezout's theorem says that when you have two conics, you're going to get 4 solutions. You may not know how many solutions there are, but just kind of be prepared that you potentially could have more than one solution. You could actually have no solutions, or you could have more than one. So all kinds of opportunities there for these things. Okay, so decimal equivalents would look like that. And what we're going to do is we're going to start our first iteration. We're going to start at 1.4x and 0.4y, and we're going to see if we can march towards that solution using an iterative process here. That's what we're going to do. So our first function value, first iteration, we put that in parens, first iteration, where I'm bringing in the 1.4 for x and the 0.4 for y. That's going to give me, once I figure out what these functions are evaluated to, it's going to give me minus 1 1.88 and minus 5.12. It just kind of happened that the one norm of this is 7. I didn't mean for it to work out that perfectly, but it kind of looks nice. And then if I take a look at the Jacobian on the first iteration, we're going to put in our 1.4 for x, and we're going to put in our 0.4 for y. So I get hard numbers for my Jacobian at the current iterate, which is 1.4x and 0.4y on that first cycle. So let's see what happens when I do what's going to end up being the Newton-Raphson technique. I'm going to get the second vector iterate is equal to the first one minus j inverse times the function value. So I've got my j, and I'm prepared to invert it right there. I didn't show the actual inverse in terms of numbers, but I'm going to take that and multiply it by my function, my first function values, the minus 1.88 and minus 5.12. And multiply that into the inverse, subtract it from 1.4 and 0.4, and I get 1.95 and 0.825. So it looks like I kind of shot past a little bit the actual solution, but I'm definitely closer to it. And the idea is that you iterate again, and you will get verily to the magic numbers there, square root of 7, square root of 7 halves, and square root of 1 half, or decimal equivalents. Okay, so that's kind of the idea, but now let's kind of take a look at the theory. So if you remember your basic univariate iteration for Newton-Raphson, you kind of have a point where you're at, and you take the slope of that point, and then you against the function there, and then that gives you an idea of what would be your next one. So this is your current x. At that current x, you have a certain f value, the f value here, and then you have a certain slope there, and you're going to use those two things to figure out what the next x iteration would be. So that's the Newton-Raphson equation. And where does that come from? Remember you've got your Taylor series, first order Taylor series expansion there. And the idea is that you want that next the function at that next x, you want that to be 0. That's what you're hoping for. So you set that to 0, and you basically just solve this equation for x I plus 1. In other words, the next iteration. So that's where it comes from right there. Okay, so that's the univariate Newton-Raphson. Now let's go remember the Jacobi method that we had for multivariate iterative root finding for a linear system. So this is where you have ax equals b. So you've got an n by n A matrix, and you have a b column, which is n tall, and then you have n unknown x values that you're trying to solve for, and you can solve for these using the this is actually Jacobi. It's a little bit of a special representation of Gauss-Seidel, but you get a d minus a c times the current x iterate, and that will give you the next x iterate column vector, right? So again, in these, it looks like superscripts, but that's just talking about the iterate. So what's interesting here is if I take like a 3x3, I can kind of think about taking that 3x3 and breaking it up into a diagonal version and then an off diagonal version. And when I do that, I'm kind of thinking about setting up for, these x iterates. So what I could do is say, well, my x iterates, they should be kind of close. So I just kind of distribute what might be kind of close. So this is an approximation, quite frankly. But if my x's are kind of close, and I just kind of split them up here, and then what I can do is take this equation and divide through by the A1, A11, A22, A33 on the per row basis. And then that's how we get the C matrix there times the current X iterate. And that's how we get the D matrix that's there. So that's where these actually come from. It's kind of similar to, going from a univariate Newton-Raphson. Now we've got a multivariate linear Jacobi method, but it's kind of looking like a Newton-Raphson right here, multivariate Newton-Raphson. And we're going to take this idea and we're going to take a multivariate array of x's and a multivariate array of functions, and we're going to put them together, and we're going to extend this to a multivariate Newton-Raphson. Okay, so the idea is that, some ith iteration, you might have an x iterate, a whole column vector of them, and you might have a whole column vector of these function values calculated at the particular x iterate xi. Okay, so you have that, and what you want is you want these functions to be zero at a particular iteration. That's what you're hoping for, is that all of the functions go to zero simultaneously. They simultaneously, quote unquote, vanish. And when that happens, the associated x, the column vector of x values, is a solution. Okay, so you might have one, you might have more than one, you might have zero solutions, and that's something we talk about in the next video, actually. Okay, so let's take a look at, you remember Brooke-Taylor. So you take maybe the first function, and you think about its next iteration, the I plus 1. Well, that would be equal to the current function, and then you have the partial of that function with respect to x1 times the delta x1. You have the partial of that function with respect to x2 times the delta x2. You have the partial of that function with respect to xk, and then you have the delta xk. And then you go all the way until you get to the n partial of the first function with respect to n times the delta xn. All right, and then you do the second function. You do that again. So whatever you did for the first function, you're going to do that again for each and every variable. So this is first order multivariate Taylor series expansion, and it's a pattern. I go all the way to n, right? So I've got all the functions. I got all the function n. I'm going to say there's n functions, and I've got n x variables. Okay, so I'm going to do that. And then I'm going to rewrite it in a matrix form. I'm going to have my current functions, all of my current functions, created as a column vector. And that's my ith iteration. I'm going to take the first function and put that in the first row. Second function, second row. So these are the partials all the way to the last function, n function. And then the columns go, per with respect to x1, with respect to x2, with respect to xk, with respect to xn. So the columns establish what the variable you're differentiating with respect to. The rows are the particular functions, okay? And then you have the delta x1, delta x2, delta xk, delta x1. So those would, come up, that column of delta x's would kind of coordinate right with their respective with respect to's, right? So they go together in the matrix multiplication sense, and the sum of those things for a first order Taylor series multivariate expansion is going to be equal to the functions, the values of the functions at the next iteration, right? So that's the Jacobian that we have there. That's my ith plus 1 functions. That's my ith functions, ith iteration functions. There's my Jacobian J. There's my my I plus 1 x iterate. There's my ith x iterate right there as a column vector. All right, so then I take that last one and I write it very, very compact in this way. Okay, and the idea, remember, is that you really want that next function iterate to be zero, a zero vector in this case. Same idea as we had in the univariate case. So you're wanting this to be zero. You want to have that x at I plus 1, you want that to be a solution. So if it were, then then all those functions would be zero, would vanish. So this is what we want. So we take that equation just like we did for univariate Newton-Raphson, and then we solve for the next x iterate. And when you do that, you end up having to multiply through by J inverse, and that's how I get the J inverse times the current function iterates. And I put that J inverse with the function iterates on the other side of the equation. And then I have a minus xi iterate there, and that goes over and becomes a plus. So that's my golden equation there for Newton-Raphson, multivariate Newton-Raphson, 1217 in the book. So that's what you use to iterate. It's very, very, very straightforward how to do that. Okay, so here's how we did it. We had our J. We had functionally our J. So the J is, from a variable standpoint, for these particular two curves, that's not going to change. It's just the x and the y's are going to change, right? And then what we do is we're going to, again, start from that x is 1.4 and y is 0.4. And, we figure out what our function values are. Remember, we've got that minus 1.88 and minus 5.12. And then we have our Jacobian. With the first iteration, we're putting in our 1.4 and 0.4, and then we get our Jacobian, and then we go ahead and implement the Newton-Raphson iteration. We get our x2, the second step, and it's going to be the first step minus the Jacobian, this matrix inverted times the current functions. I get that 1.95. It just kind of shot past a little bit, but then it comes back very quickly. Okay, so here's some code that I wrote, and I'm going to kind of show you how I do contours, because I do this in MATLAB. First of all, I set up an x vector that goes from -4 to +4, 200 of them. I do the y vector, same kind of thing. But the way I do the contours is I want to do a mesh grid. So it's going to take the x vector and the y vector, and it's going to create basically a matrix of x and y. The matrix X contains all combinations of x and y. So these are going to be all x's and all y's. So end up with, in this case, it would be a 200 by 200 grid of xy pairs. So the x and y are matrices, and then when I do that, what I do is create a Z1 matrix. It's going to be all of those respective x's plus all of the respective y's, each one squared minus 4. So this is creating a 200 by 200 grid Z1 that contains all possible combinations of these x's and y's. And I repeat that for the ellipse. And then I do a contour. And the way you do the contour is you give it the x matrix, you give it the y matrix, and then you give it what you want for the contour. And I only want to show where the contour is going to be 0. So that's why I put 0, 0, show it in red. Repeat for the ellipse, show that in blue. And then I've got a little cheater draw circle. I just wanted to draw a little circle at a particular place. So I'm drawing it at 1.4.4 where I start. And I give it, I think, a radius there. I go with green. And then there's going to be the solution that I show. Okay, so here's kind of where I'm going to, the meat, here's the meat is going to be in to solve my equations. So the solve my equations function is going to take that starting point, the 1.4 and 0.4, and it's going to create a path from 1.4 and 0.4 towards towards what will be the solution. So that's going to, let me show you how to do that in just a minute. But the result of that solve my equations is going to give me a path. It's going to start at this position, and then it's going to just give me a connection of line segments over to where the solution is. And it's going to, for each iteration, I would get a point on the path. So it's going to be a line path. And that's why I call line path all rows, first column. It's going to be my X's, path, all rows. Second column is going to be my Y. So that what I need to return here is going to be, it's going to have two columns, an X column and a Y column. And then the number of rows corresponds to how many iterations. I show some ticks to turn the grid on. And this one's kind of important because if I don't put that, then I'm not going to get a true circle. It's going to be really two ellipses. So I get the aspect ratio right. So that's how the function that kind of draws the pretty pictures works out. But the meat and the potatoes here, when you're looking to solve, when you're looking to iterate, you've got, as I've always showed you guys how I do it, I do a one norm of some function, some vector function. That's what we're going to do here, one norm of some vector function. And when that one norm, that's a scalar, one norm. Once that scalar gets down below a certain threshold, I call it the times eps. So eps is a very, very small number. So is going to really be representative of the number of floating point operations. We'll look at that in just a second. But once I get past that, then I've satisfied to within floating point error. Anytime in here I could stop, but I'm actually going to stop. Once I get past a certain, once the polishing of the X's. In other words, there's no additional improvements. The X's aren't changing, or there's just no additional improvements. So remember, that's what this is saying right here. The book, I call this historically with you guys, I call this the book polishing. And then this part here is saying that the function values are 0 to within floating point round off. Okay, so let's go take a look at the code. Solve my equation. So I'm bringing in XS and YS. So those are kind of my start positions. And then I'm just going to assign them to some local variables, X and Y. So I've got something handy to kind of manipulate. I don't want to manipulate the start positions. So I've got X, Y, and I'm going to go ahead and create my Z that I'm returning as my path. So I'm going to go ahead and create that very first row, right? So my Z is going to have that row. And if you kind of sneak a peek down to the bottom, what I'm going to be doing is taking the previous Z, and I'm going to be concatenating another row. And somehow or another, I got to figure out how to get this XV2. So that's what it is. So the Z is kind of handle, collecting every time row of the whatever iteration. All right, so I've got a for loop. I go 1 to 100 like I do a lot of times. And I'll just set it 1, I'll start the iteration at 1, and I'll try to go to as much as a high number. But really, I want to break. So I've got to figure out how to break. What does it take to break, quote unquote, break out of this for loop? And how many times will this run? So that's what we're going to find out. It's pretty fun. Hope you're enjoying this. So there's my Jacobian, 2x, and then 2y is my first row, 4x and 12y is my second row. No, nothing, no magic here, just the J that, we kind of did. This is my FV. So FV1, so that's the vector function, or the vector of functions. There's my first function. There's my second function. I've set it up as a column, a column vector. And then I've got the x squared plus y squared minus 4. That's the circle of its root. There's my 2x, 2 times 2x, 2x squared plus 6y squared minus 10. That's that ellipse, right? So there's my vector function, and it's actually going to calculate it. So FV1 is going to be a 2 by 1. It's going to have hard numbers, right? And my J is going to have hard numbers because X and Y are established. They're initialized, coming into the loop, and they're going to be refreshed at the bottom of the loop for the next iteration. So J and FV1 all kind of make sense. Let's talk about okay? Let's talk about So is going to be representative of the number of floating point operations, but also sort of the magnitudes of them. So you see I've got abs everywhere, right? So it's always, you're always adding a positive value. Even when it's -4, it's going to be a +4. I got a -10, it's a +10. And I've got abs of x, so x is, if x happened to be negative, that abs is going to take care of it. Everything goes positive on these things, right? So I've got abs x squared, I've got abs y squared, and I'm doing a 3 multiply here and a 3 multiply here. The reason is the number of floating point operations that's going with that particular first term. I've got x times x, that's 1. That's one operation. And then I'm going to be adding it to y, whatever happens on that term, and I'm going to be adding it to whatever happens in this term. So there's 3 floating point operations for that term. Similarly, for the y, you're going to do y times y, so that's 1. And then you're going to add it to the x term, that's whatever happens there, that's 2. And then you're adding in the 4, that's the third. Now this 4 term, it's only in the very end, so it only sees 1 op, so there's no scalar in front of it. And then similarly over here I kind of put, the parens around that just so kind of to identify that goes with that first one. And then I add in, what's happening with the ellipse. Now the ellipse gets an extra thing here because there's a 2, there's x times x, then there's a times 2. Then you're adding it to the other 2 terms. So there's actually 4 floating point ops that go with those particular first 2 terms. So that establishes my I'm going to get my xv1 is my, the current iteration, the ith iteration. And I'm going to figure out what the next iteration is. xv2 is what I'm calling it locally. So that's going to be the current ith iteration minus J inverse times my current FV1. So there is Newton-Raphson right there. It's very, very simple. Very simple, straightforward. So my xv2 is going to be my next x values, and I'm going to go ahead and subtract from the next minus the cur, and then I'm going to divide by the next. So that's looking at my x's. So that's going to be an array of 2 of them here, column vectors, and that's going to be my eps a. That's going to be, this array right here, the relative changes in x values. So that's what that is. And then I'm going to print out some stuff. I'll come back to that in a second. But what I want to do is I'm checking the book polishing first. So if the infinity norm of eps a is less than that book polishing thing, I've got one condition satisfied. That would be this one. And if I have a norm of FV1, the 1 norm, so that's the sum of absolute values, 7 in that first case we did, right? If that's less than times eps, so that is this condition that says a floating point round off is satisfied, is 0 to within 4 floating point round off. If both of those satisfied, you're breaking out of this bad boy. If it's not, then you're going to set your x and y to the current xv2, current xv, the current xv2 item 1, which is your x, and item 2, which is your y, that we got from that implementation of the Newton-Raphson. And then you're going to take the xv2, which is a column vector, you do a little transpose of it, and you append it as a new row. Okay, let's go take a look at the printf and make sure we understand how this all kind of works. So printf, so the %0 3d, so that goes with the first variable, I, so it's going to give me an I count. It's going to give me a 0 in front. If it's less than 3 digits, it's going to 0 fill in front, but it's going to give me 3 spaces for a d means a decimal integer. Then I'm going to print out the percent. says that that's a formatting specifier. So a field of 8 with 4 after the decimal place. F means a double float. So that's going with X. Repeat for Y. Then I'm showing the floats, or the function value 1, function value 2. They're there. Field of 10 to 6 decimals. And then I'm showing to 4, a field of 10 to 4 decimals. And then I'm going to show the how the X's are polishing. So I'm doing that as a norm. And I'm going to go 16 decimals. And then I'm going to give a Boolean. It's going to be a 1 or 0. The %1D means it's going to be a space for 1 decimal right there. It's going to be inside parens. So that's going to be a true false. True is 1, false will be 0, whether the current polishing is less than the book polishing threshold. And then I'm showing the 1 norm of my functions in to 16 digits after the decimal. And then I'm doing whether that 1 norm is less than times EPS. Okay? So I've just walked through that very, very slowly, and hopefully you got that. But that's the same thing we really did very early on in the univariate rooting technique. Very much the same thing. Okay, so here's what happened. It only took 6 iterations. I started at the 1.4.4. Remember, there's that minus 188 and minus 512. That's what gave me that perfect 7 for my my 1 norm of the functions, as I said earlier. There's that second iteration of that point that shot past, right? It shot past. And then eventually I got down here to where I have minuscule error. It's to within floating point, and it's also not changing in X. And my is like 66. But times EPS, my function value is less than that. Okay, so you see a full view here of what's going on, and then you see kind of a close-up view here. Okay, in summary, we started with an example. We remembered our univariate nonlinear rooting algorithm for Newton-Raphson. We looked at our multivariate linear iterative methods, and we kind of extended that thought process to a multivariate nonlinear iterative method. And then that was multivariate Newton-Raphson. We brought in the Jacobian, and then we finished up with that straightforward example. So I hope you enjoyed it.